This is a very exciting day in your statistical career because we start statistical inference. You're supposed to, hey, what does that mean, statistical inference?
Learning things from statistics.
Remember the very first week of class? I said there were basically three areas of statistics. One is design of studies, design of experiments. Thing does not want to follow me. The second is descriptive statistics. So we did design, and then we've spent a lot of time on descriptive statistics. So today we get to start statistical inference. So, to start, what the heck does that mean? Statistical inference. Stephen?
You're looking at stats and coming up with answers from data.
Okay, good. Answers to what though? He said we're gonna collect data and then look at that data to come up with answers about
your hypothesis.
Okay, the hypothesis. But why do we collect data? Right? Why do they draw samples?
Just to figure out information based on population.
Okay, figure out information about the population, but why don't they just measure the whole population?
That's hard.
Because it's not hard, it's sometimes impossible, right? You can't do that. So you take a sample and you try to make inference to the population. That's what we mean by inferential statistics. Using sample data to draw conclusions about the population. And when we say in statistics about the population, it means about some parameter of the population, about a population parameter. Okay, so this is your spreadsheet that you all sent me at the beginning of the semester. So we're going to start looking at some data there. I have to scroll up to the top to remember which column is which. But I'm interested in the pulse. So that's the column I. Everybody got that? I'm going to scroll down and there we go. There's two samples from the D section, you guys, in a row. So that'll give you, if I pool you guys together, that'll give me a sample of size 10. There's nothing magic about wanting 10 instead of 5, except bigger samples are better. Right? So now, who are these people? LJS, Laura. Right? So Laura gave us these 5 pulses. Wow. What do you notice when you look at her 5 pulses?
Fairly similar.
They're fairly similar, and they're also fairly low, right? In fact, I'm going to let the cat out of the bag here, but in real research, you will never know this. So what I'm going to do is I'm going to treat all 365 observations in this data as my population. And then I'm taking Laura's and whose was this one? DJM. All right. So you go by Dora, right? Dora Lynn. Okay. So Dora Lynn and Laura, I'm going to pool them together. Okay? Kind of interesting. What do you notice about Dora Lynn's? Okay, a lot more variability, and also 2 fairly high values that are going to offset all the really low values over there, right? So again, part of the reason for pooling 2 samples together is because any bias in one sample tends to average out with the bias in the other sample, right? So, if I look at all 365 observations, the overall mean is 72.4. Let's see what the mean is of those 10 values. So get out your calculator and put these 10 values into L1. And I'm going to read them out loud for the purpose of the video here because I don't think they can probably see those. But go into your list editor, get ready to go, and I'm going to start reading them, and you may have to tune me out. So the first one is 68, 54, 58, 62, 56, 64, 85, 104, 106, and 88. First one is 68, yes. Then when you get them entered, I want you to go to one-var stats and compute the sample mean and sample standard deviation of those 10 observations. Alexis, you looked up first. Are you done? Mm-hmm. What'd you get?
74.5 and then 19.7.
Wow, 19.7. Okay. That's pretty big standard deviation, but we kind of saw that. Laura's were all pretty small numbers, and Dora Lynn's were all pretty big numbers, so there's going to be a lot of spread. So this is a pretty big estimate of standard deviation. What is the population standard deviation, you may ask? It happens to be about 12.5 if I round to one decimal place. It was 12.46 something something, right? So what we're going to do is we're going to pretend like this is real research going on, and in real research you don't know these values. You don't know the population mean and standard deviation. That's why you're taking the dang sample. That's why you're doing the study, because you're trying to find that out. So now they're in a black box. You can't see them, right? So we have no idea what the population mean is. We have an estimate of that from our sample, right? So the sample mean is our best estimate of the population mean. And that estimate is called a point estimate. So X bar is a point estimate of mu. Now, if I'd left the word point off of that and just said X bar is an estimate of mu, you all would have went, yeah, good, makes sense. But now I threw this word point in there. What does that mean? Well, it means it's a single point on a number line. So if I draw a number line and I put the true mean value, which we don't know what it is. Remember, it's hidden from us. But let's put it there, 72.4. Where does 74.5 go? To the right. It's bigger, right? But how far to the right? Well, let's see. Didn't we learn something recently about the spread in possible values of X bars? What's that called? The distribution of all possible values of X bar. No, it's not the range, the distribution of it. What's that called? You guys just had a test Friday, right? What'd you do this weekend? Kill every brain cell that had a statistic in it? Don't do that. Right? What's the sampling distribution of X bar? That's what I'm trying to get you to say. Sampling distribution. What is it that gives us the sampling distribution of X bars? Okay, let me rephrase the question. What theorem is it that gives us this? The central limit theorem. Very good. So the central limit theorem tells us that all of the X bars will have a normal shaped distribution. It'll be centered at the true population mean, which we don't know what that is in practice, but today we get to know that. So where does 74.5 fall? How far is it out here, or is it real close? Where is it?
close to the right.
Okay, be fairly close. Well, how close? And what am I trying to get you to think about? Standard deviation. How spread out is this distribution, right? So where is 74.5 in relation to this graph? Well, halfway, I'm going to redraw this side of it because it got a little too vertical. But, so it looks, that's even worse. But about halfway down the hill would be, how far out?
84.9.
Okay, where'd you get that?
Standard deviation plus the...
Okay, which is sort of right but not right. Because what did he do? He gave me 84. He added one standard deviation. But this is the sampling distribution of X bars, not the population distribution of individuals. So what do you got to do to this number? What'd you say? No? What's the spread in the sampling distribution? By the central limit theorem. Come on, Jacob, you know this. From the central limit theorem, what does it tell us the variability in X bar will be? I'm not looking for a number. I just, what do you do to get that?
Oh. Is that and then it's divided by how many?
Exactly. So the standard error of X bar is equal to sigma over the square root of n. Right? So that's 12.5 over the square root of 10. Give me that as a decimal.
3.9528.
3.9528, I'll call it 953 is close enough. Now add one of those to 72.4, and that tells me where this dotted line is. Right? One standard error from the mean.
76.35.
So 76.35 is that. So now, where is 74.5, which was our sample mean? We had X bar equals 74.5. Now we can anchor it. We know where that falls relatively, right? So it's about right there. So 74.5. Right? So that's a pretty good estimate. It's not too far out. The one we got in my last class was 62.5. Where did 62.5 fall? Way out there, right? It's a long ways, but actually it's not that far out. It was not quite too out. Well, how far out is that value? How far away from the thing we're trying to estimate did that sample estimate fall? And by the way, the units I want you to use are number of standard errors. How many standard errors was our sample mean 74.5 away from the population mean of 72.4? What is it that we compute that gives us number of standard errors? Z-score. So the Z-score is 74.5 minus 72.4 divided by the standard error, which is 3.953. Give me that. What? 0.5312. So not even, well, about half of one standard error. Okay? That's pretty close in. So congratulations, you guys. You gave us a good sample when we pooled it together. Right? Now, if researchers are doing a study and they collect some data and they send it to me as the statistician to analyze their data for them, they'll say, in the end, something like, "Hey, Mr. Statistician, what's the population mean?" You know how I'm going to answer that question? I don't know. That's how all statisticians answer questions. Right? But you have to understand, that when you take sample data and you compute the mean from your sample, you did not get it right. Guaranteed, you're going to be off a little bit. The question for statistical inference is, how much are you off? How much error is there in that estimate? You've been watching the... What's that?
It depends on how large the population is.
It does. That's very good. It depends on how large the sample is. If N is big, standard error gets small. Right? So you watch the news these days, and they're always doing the political polls about the primaries and all that. And Donald Trump has 27% of the Republican vote, whatever it is. And then down the bottom in the fine print, it'll say, margin of error of plus or minus 4%. Where does that number come from? Comes from the standard error. How much error is there? Right? Now, the margin of error is closely linked to this standard error, and we're going to show you how to compute it in just a second. But this idea, I'm going to come back to this idea of a point estimate. A point estimate of mu, 74.5, is a single point on a number line. But I know that isn't going to be exactly right. So instead, I want to use this concept of margin of error to give an interval. And say, well, I know it isn't exactly 74.5, but it's almost certainly between here and here. And I'm going to start with my point estimate, and I'm going to add and subtract this idea of a margin of error. Right? So x bar plus and minus capital E. And that capital E is called the margin of error. This gives a confidence interval. That's what it's called, a confidence interval. Or more generically, an interval estimate of mu. I should say for mu. Confidence interval for mu. Okay? So if I told you that the margin of error from this sample was about 8, which is just roughly in my head, that's about what it's going to be. It'll be a little less than 8. But margin of error, well, actually, I'll come back to this, and I'll lead you towards that 8 that I just got, approximately. If I wanted to be 95% confident that my interval contained the true population mean, think back to this picture. How far do we go to get 95% of all x bars? 2 standard errors, right? So if I go roughly 2 standard errors, I should have 95% of all the possible x bars. So then if I take that distance, 2 standard errors, and I add and subtract it to my x bar instead of to mu, it's still going to capture or contain this true population mean 95% of the time. Right? So let's do that. Margin of error is equal to, I'm going to put approximately equal to, because this is not exact yet. We're going to make it exact in a second. Approximately equal to 2 times the standard error of x bar. Right? So 2 times 3.953 gives you what? 7.906. Okay? And I guess we'll go ahead and keep 3 decimal places of accuracy. So there's my margin of error. Now we're going to firm that up for you in a little bit. Now form the interval. Take x bar, add and subtract that margin of error, and give me the interval. And I will tend to write intervals in interval notation with lower bound, comma, upper bound, all in parentheses. But you could also do it with less than symbols, you could go like that. So it's an interval for mu. Mu should be between whatever number goes here and whatever number goes there. Either way is fine. All right, so x bar is 74.5. So that's 74.5 plus and minus 7.906. Anybody got those numbers for me?
66.594.
66.594.
82.406.
82.4 what?
06.
06. Okay? Now, let's come back to that question they asked me. So, Mr. Statistician, what's the population mean? I don't know. But I'm 95% confident that it's somewhere between 66.59 and 82.4. Right? So remember, being a statistician means never having to say you're sure. We get to say things like that and get away with it. I'm 95% sure that it's in here. Now, this 95% that I've been throwing around is what dictated that number. How many standard errors? What if I wanted a 68% confidence interval? I'd go one standard error. What if I wanted a 90% confidence interval? Ooh, now I have to find a z-score, right? But that's all this 2 is. It's a z-score. How many standard errors, right? And in fact, this 2 is not exactly right. So I said we're going to have to firm that up. Let's do that. Let's take a standard normal distribution. Which is centered at 0. Z-scores. And figure out how many standard errors would I need to go in order to get the middle 90%. So we'll call that negative z and z. Right? So this is called the 0.90 is called the confidence level. Right? So you decide that before you ever do the study. I want to do a 90% confidence interval or a 95% confidence interval. Whatever it is. Right? So that level of confidence we'll denote by C. Now I will not get picky whether C is written as a proportion, 0.90, or a percent, 90%. Your calculator will get picky. You put in the 90 and it's going to go haywire. All right? So you need to always convert it to a decimal. But the level of confidence is C, and then a confidence interval is formed from that level of confidence, which then dictates what the margin of error is. Okay? So the margin of error, let me do it under here. The margin of error is equal to the Z critical value. So the book writes this as Z alpha over 2. I'll explain the alpha in a second. But I like to write it out. I'll start abbreviating as Z crit. Understand crit is short for Z critical value. The critical value is just how many standard errors you need to go to have that level of confidence. So that's where that 2 is sitting over there. That's my Z critical value, right? And then times the standard error of X bar. That's what a margin of error is, right? So it's the same thing we did over there. I got a 2 times the standard error of X bar. Well, now it's Z critical to take on any confidence level, right? So this alpha thing. There. I knew there was a slide in here like this. If the area in the middle of the curve is equal to C, the confidence level, then 1 minus C is the area that's not in the middle. Everybody following me? Right? And now 1 minus C, they call that alpha, which is the Greek letter A, basically. Greek alpha, right? And that is an air rate. Alpha is an air rate. So if I get it right 90% of the time, then I get it wrong 10% of the time. So alpha is called the air rate. You with me? So how much area is in this tail? Alpha over 2. Alpha over 2, which is 1 minus 0.9 over 2, which is 0.05. We did this before, remember? We just didn't know we were doing it for this reason. And in this tail will also be 0.05. So now I want you to use your calculator and tell me the z-score, the value of z, that'll contain the middle 90%. You had a question just like this on the test. Right? Only it wasn't z-scores. It had some other distribution, but it's the same idea. So go, do it. I want to know what does z need to be so that when I go to negative z to z, I have the middle 90%. Lindsay, get your calculator out. Quit daydreaming. Anybody got an answer? If you round to 3, it should be 645. Is that? Does yours stop at 3 or? Yeah, there you go. See, the next one is an 8, right? So 1.645. Anybody getting that? Now, let's be honest. You had a test Friday. You had to do this kind of thing. But probably half of you are going, I don't know what to do. What function are you using? Inverse norm. Very good. You guys are so much better than my last class. None of them could remember what... I mean, 0 of them could remember. So z is going to equal inverse norm of what? What do you put in there? What'd you say? 0.45? That won't do it. You could put in 0.9501, or you could put in 0.0501. Yeah, you were going for like the tables in the back where you split it in half. If you use this one, which I think is the easier one to use, 0.05, because then you just look at the tail area and you enter it in, you'll get a negative in front of it, which is fine. Then you just ignore the negative, right? Because you're plus or minus anyway. So the z critical value for 90% confidence, z equals 1.645 if you go to 3 places. Is everybody able to match that on their calculator? Okay, good. Now you do 95%. Now we already said 95% should be really close to 2, because we used a 2 over there. But it isn't going to be exactly 2. Tell me what it is exactly to 3 decimal places. Good. 1.960. Now raise your hand and don't be shy. Raise your hand if you weren't sure where the heck, if you can't get that. Does everybody know how to get that? Okay. What do we do different here? When I say 95% confidence, this C becomes 0.95. So I'm just going to erase, not redraw, but 0.95. So then alpha becomes 0.05. So half of alpha becomes 0.025. So then in the 2 tails, or 025. So now here you enter 025. So I always just say it's half the leftover area, or half the leftover confidence. Right? So 0.025 should be 1.9599 something, 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 and it rounds to 96. Right, now you do 99%. Half the leftover area. Good. 2.576. Everybody understanding how to get these? Now these three are what I call the big three. 90, 95, and 99% confidence. Those are the ones that get used in practice. I started to say 95%. This one gets used in practice 95% of the time. Almost always we do a 95% confidence interval. Once in a while we'll do 90, once in a while we'll do 99, and pretty much never do anything different. But on the homework, they're going to ask you to do odd ones like 98% confidence interval or 96% confidence. But now you know how to get the critical value. You just put in half the leftover area into your inverse norm, and you'll get the critical value. Okay? So now the only thing we would do then to fix this interval that we did a minute ago was change this 2 to a 1.96. We'd have a slightly different value there. Add and subtract, we get a confidence interval. Okay? So now, do for me a 99% confidence interval. You do it yourself. Using the same numbers for this sample size of 10, and 99% confidence. Now that you know what the critical value would be. You already got it? You think so? Okay. I won't have you shout it out yet. We'll wait and let people catch up.
Is that not what we're supposed to be doing?
Mm-hmm. So there's your critical value, but this needs to be multiplied by the standard error.
Oh, we're doing 2.
Let's see, the standard error is 3.953. This critical value just tells you how many standard errors you need.
Okay.
Right? Okay, is everybody understanding? Or are you stuck?
I'm stuck.
Yeah, what you're doing here is actually what we're going to do in the next section. But I want, instead of the 19.7, which came from the sample, use the 12.5 that came from the... But other than that, you have it right. Okay, that is right. Got an answer?
Yeah, I used wrong.
Yeah, you don't need the inverse norm function now. That only gives us the 2.76. So what you'll want to do is put in 0.995 or 0.005 to get the critical value. But then once you have the critical value, just do x bar plus or minus e. You guys getting it?
Yeah, I was just restarting it.
Okay. Okay. You're confused too? Okay, all that we do now is we first have to find the margin of error, right? So we found over there already that 99% confidence, the z critical value would be 2.576. And then the standard error of x bar we found over here, up there in the upper right corner, is 3.953, right? So then you multiply those together and then just add and subtract them from x bar. Yeah. right? Okay, so first thing to do is to figure out what your margin of error is. Come on, boy. Okay, so margin of error is covered up. No, here it is. Margin of error is Z critical value times standard error. The Z critical value for 99% confidence is 2.576. So 2.576 times the standard error of X bar. So based on a sample size 10, the standard error we computed earlier as what? 3.953? So you multiply that out to get the margin of error. So tell me what that is. 10.18 if we stop at 2 decimal places. Okay? And then now to get the confidence interval, how do we use the margin of error?
Plus and minus.
Plus and minus. So our sample mean was 74.5. So we have 70, that's not a 7. 74.5 plus or minus 10.18. Okay? And that gives me an interval, if I put it in interval notation, of 55 point something. What is it? 55 point?
64.32.
Oh, I'm sorry. I was remembering last hours. They had different mean. What is it?
64.32.
64.32. 84 point what? 68. Okay? Now look at that interval. There, everybody able to match that finally? Okay, look at that interval compared to this interval. What do you notice? It's larger. It's a wider interval, right? Does that make intuitive sense? Yeah, remember what a confidence interval is. It's an interval of numbers that we are highly confident, in this case 99% confident, that the true population mean falls in there. If I want to be more confident that the true mean is in here, I got to put more numbers in there. I got to make it wider. If I shrink it down and I start throwing away numbers, pretty soon I'm less and less confident that the true one is still in there. Until eventually, if I shrink it all the way to nothing, I'm down to a single point estimate, and I'm 0% confident that the true mean is that. Right? So you need this idea of margin of error to give you a feel for the degree of precision there is in your point estimate. Here's my point estimate, but it's going to be off by no more than this. Right? That's confidence interval. Okay, so now back to this idea of the width of a confidence interval. Let's say we stick with 95% confidence. So that's this interval, 66 to 82. Can you give me a confidence interval that has 100% confidence? People ask me this. I mean, and seriously ask me. They're not joking. Why are you doing 95%? Give me 100% confidence interval.
Can you get to 100%?
Can you get to 100% confident? Sure you can. Remember what I'm looking for here. The mean pulse in the population. And I am 100% confident that the mean resting pulse is somewhere between 0 and 1,000. I'm 100% sure of that. Or, to say it another way, negative infinity to positive infinity. I'm 100% confident the true mean is in there. And then they roll their eyes at you and they say, okay, but that's not useful. Right? It's true, but it isn't useful. So the level of confidence is a balancing act. I want to be highly confident, but still have an interval that's narrow enough that it's useful. That it narrows it down to something that I can take advantage of. Now, what do you think about 66 to 82? I'm 95% confident it's 66 to 82. That still doesn't narrow it down a whole lot. It's a lot better than 0 to 400, or negative infinity to infinity, but it's still pretty wide. What can I do if I stay at 95% confidence? What can I do to make that interval shorter?
Higher population.
You almost had it.
Sample.
Sample, good. A higher number in your sample. If I increase the sample size, how does that decrease the width of the confidence interval? It decreases your standard error. Look at the standard error function. Sigma over the square root of n. If n gets bigger, standard error gets smaller. So the confidence interval will shrink. So that's our last topic for the day, is how do I decide how big a sample I need? Let's see, we did 95% confidence, and we had a margin of error of, I was pushing this over to see it, and I guess we never did, this was with a 2. Redo this with a 1.96 for me. So for 95% confidence, 1.96. What is that margin of error? And it's going to be the width of this confidence interval, or half the width. 7.75. Okay? Let's say I come back after the study and I say, you know, that's really not quite accurate enough. I want to be within 2. That's within 7.75 in either direction. I want to be within 2. How big a sample do I need for that? Well, what I'm saying is I want the margin of error to be 2. Right? And you know, I'm pretty good at algebra. So if you think about margin of error, there's the margin of error. Right? So I wrote this a little too high, but here's the formula for margin of error. Z critical value times the population standard deviation divided by the square root of n. You tell me what E is on this side, a 2. You tell me what confidence level you want. I know what Z is. I know the population standard deviation. I can solve for n. It's just algebra. Now, I'm not going to take the time to go through the steps of the algebra. Well, what would you do? Let's put it up under here. 2 is equal to Z critical value times sigma divided by the square root of n. How would you solve for n? What'd you say? Okay, cross multiply, right? So you're going to multiply through by square root of n. Then you're going to divide through by the 2. Then you still got n under square root, so you got to get rid of the square root. So you square everything. That's all there is to it. So here's that formula. Somewhere. There. I knew it was in here somewhere. So here's that formula. N equals the Z critical value times sigma divided by the margin of error. And then the whole thing is squared to take the square root off of n. So compute it for me for 95% confidence. So if I want 95% confidence, what sample size is needed? For a margin of error of 2. Now, sometimes the homework problems will word it like this: for a margin of error of 2, and sometimes they'll try to trick you, and they'll say something like, so that you can be off by no more than 2. Or you'll be in error by no more than 2. And just recognize, oh, that's margin of error. You use this one. Right? I forgot to say it at the beginning of this section. This section 8.1, everything is done assuming that the population standard deviation is known. In practice, it's never going to be known. But it's where you need to start in order to understand things. And then Wednesday, we move into, okay, what if it's not known? Well, if it's not known, we just use the sample one, but it throws a wrench in the works a little bit. So we'll do that on Wednesday. But finish this out. So what is the Z critical value that I need? I said finish this out, but I meant finish this out, right? This form is this one manipulated. So N is equal to 1.96 for 95% confidence, right? Times 12.5, that's my population standard deviation, divided by 2. And that's the margin of error that we want. And this is done before you've ever collected the sample. Duh. You can't go collect the sample and then figure out what sample size you need. So you figure it out before you go, and okay, now I'm going to go out and collect that many data on that many people. And then you square it. So what do you get there? $150? Give me 2 decimal places. 150.06. Okay? Is everybody matching that? So with a sample size of 10, we had a margin of error of 7.75. If I want to shrink that all the way to 2, that's a lot smaller than this. I'm going to need a lot more subjects. Now, I can find 150 people fairly easily. But this 0.06 guy, where am I going to get that guy? What this says is you need slightly more than 150 people. So you need 151 people. So N equals 151. This particular author insists that you round up to the next whole number, even when it's barely above. Some books say round to the nearest whole. It really doesn't make a whole lot of difference. 151 versus 150, that's not going to affect your margin of error much, right? But we'll stick with what the author says, because this is what they'll expect on your homework. Round to the next whole number bigger, even if it's barely above 1. Okay? All right, we will see you on Wednesday. You have no homework due tonight. It's a benefit of having taken a test. So we'll see you Wednesday.